So hello, welcome to the last lecture. It's the end. We've hit it. Yay, I guess. But guess no, definitely yay. I'm ready for this semester to be done. I hate teaching online, as I have said before. But yeah, here we go. We got it. Today I'm going to do practice problems from chapter 12. Of note, the first problem, the second problem, and the third problem are all old exam problems. The fourth and fifth are not. I have some thoughts on that third problem. I'll come back to that. Um, but yeah, the fourth problem on your exam will be something where you got two objects at different temperature, you put them together, you find the final temperature. And on this packet, the first, the second, and the third are all like that. Some with ice, some without ice. And since on the exam they might involve ice, I might not. And so I'm just going to jump right in to this first one, unless there's any questions before I go. Okay, I'm just going to jump right into this first one. That says, for the creation of Stormbreaker, what happens is there is a red hot axe head that is combined with a hunk of alum / wood. And I say that we have a piece of metal with a mass of 19 kilograms heated up to a temperature of 1.33 times 10 to the 5th degrees Celsius, worked out by the temperature of a stall, which is how it's heated. It's then combined with some wood, which has a mass of 1.39 kilograms. That's at room temperature. Given some specific heats, the specific heat of the metal is 452 joules per kilogram degree Celsius. Specific heat of the wood is 2410 joules per kilogram degree Celsius. Given those specific heats, when Groot goes and grabs this axe head, when this hunk of living wood touches this piece of metal, if they reach thermal equilibrium, what is that final temperature? What is that thermal equilibrium? Now, when doing these problems, the whole thing is going to be based off heat. Heat, by nature, is change in thermal energy. And really, energy conservation says energy shouldn't change. And since heat is a change in energy and energy shouldn't change, that means the total heat of something will always be zero. Now, in this case, we have no phase changes. We got solid metal, we got solid wood, and the solid metal, solid wood are combining to make one thing. And so the only thing I have happening is I have the heat lost by the metal. I spelled metal wrong. And the heat gained by the wood. Well, if there's no phase change, the heat gained and lost would be mc delta T, as I have written on the upper left side of the screen. Now, since I have heat, I don't really like that pen. I'm going to use a different one. Since I have the heat of the metal and the heat of the wood, that means in this equation, I'm just going to use both and say the heat of the metal will be the mass of the metal, C of the metal, T final minus T initial of the metal. And the wood, which would be the mass of the wood, C of the wood, T final minus T initial of the wood. That is what equals 0. Now, one thing I didn't say explicitly, but I drew, is I didn't say T final for the wood. I didn't say T final for the metal. I just put them both as T final. Because if two things are left together, they will eventually hit thermal equilibrium. And at thermal equilibrium, the final temperature would be the same for both. And so my goal is going to be to solve for that, solve for that final temperature. Now that's a little complicated because, there's two of them here. If I want to solve for that final temperature, I got to solve for both of those final temperatures. And how I'm going to solve for that final temperature is I'm going to factor this through. When I factor this through, I get the mass metal C metal T final minus the mass metal C of the metal T metal initial. And I'll add that to the mass of wood C of wood T final minus the mass of wood C wood T wood initial. Now, on this, I have two tomes with T final in them still, and two tomes without T final. So I'm going to take my tomes without T final and move them to the other side. Okay, I'm going to turn off the autofocus for a little bit because it keeps trying to change the focus. I'll then take this left side and factor out a T final. And the right side didn't change, so I'm not going to bother writing it again. And I'll divide both sides by everything in parentheses. I'm off the bottom, off the bottom. When I do that math, I get 95,674 degrees Celsius. Or put it in sig figs, 9.57, 1, 2, 3, 4, times 10 to the fourth degrees Celsius. So, stupidly hot. But I mean, we started stupidly hot, so I don't think it's that surprising. I've said before in the exam, if you jump straight to this step and don't show any steps leading up to it, I will not give credit for that. I'll only give credit for the final answer. I do want to see work. The homework has a bunch of these. Don't forget your last homework due Sunday. I know a lot of people have already started it. A lot of people have already finished it. Any questions? Should I go to the next page then? Let's see. This one does not involve a phase change. Sometimes they do involve a phase change. And this problem is one of the few phase change ones I wrote that doesn't involve alcohol somehow, since I have a problem. And it says, on a hot day, you pour yourself a glass of soda and ice to cool it. Let's say you have 390 grams of soda, mass soda. Well, I'm going to put that in kilograms, 0.39 kilograms at 25 degrees. So it's pretty hot, actually. Temperature of soda initial is 25 degrees Celsius. And we add to it 37.4 grams of ice. The mass of ice is 0.0374 kilograms. That's at 0 degrees Celsius. What's the final temperature? And I give a bunch of constants. I'm not going to bother writing down the constants. They're written right there. Come on, focus pedal. The idea is still the same. We're still going to say Q total equals 0. It's just the Q total here has some more parts to it. Because now what I have is ice that's mixing with soda. What's going to happen is the ice is at 0 degrees. If the ice was cold in the 0 degrees, it would be a lot more complicated. So the ice at 0 degrees will melt. So we'll have the energy required to melt the ice. But once the ice melts, it's going to become water at 0 degrees. That water is going to heat up. And meanwhile, that's going to pull energy from the soda, which is cooling down. So we have three things: the ice melting, the what once was ice is now water heating up, and the soda getting colder. And that's what's going to equal 0. And so I'll just write out the equations. For ice to melt, that would be the mass of ice times the latent heat of fusion of ice. For what once was ice is now water to heat up, that'll be the mass of ice, the specific heat of water, times T final minus T initial. Now the T initial was 0 degrees, so I'm just going to leave this T final, because T final minus 0 is T final. And then we have the soda cooling down. Mass of soda, C of soda, T final minus T soda initial. Just like last time, I want myself a T final. I got 2 of them, so just like last time, I'm going to factor it out. I have 2 T final terms, so I'm going to take everything else and move it to the other side. Okay, let's try that again. Just like last time, I'll factor out my T final. And just like last time, I'll divide everything in parentheses. To which I'll plug in my numbers. 0.39 kilograms times 4100 joules per kilogram degree Celsius times 25 degrees Celsius minus 0.0374 kilograms times 3.33 times 10 to the 5th joules per kilogram over. I switched the order of these, okay? 0.0374 kilograms times 4186 joules per kilogram degree Celsius plus 0.39 kilograms times 410. If I involve ice or any phase change, make sure you include the ML piece. If I don't include a phase change, don't include the ML piece. But either way, Q total will be 0. Questions? Okay. I'm going to leave this next tiny bit to a vote to the 4 people in the room. The next thing on this packet is this problem here. I really liked this problem, so I added it to the packet, but it was also on last semester's final, which means I solved this problem and recorded it on Tuesday. And if you want to watch me solving this problem, you can just go back and watch the video of the final exam review. So for the people in the room, do you want me to just do the same problem again, or do you want me just to skip it for now and say, hey, you can watch that video again?
You could skip it.
Cool. I normally wait like a full year to put problems in the packet for mode exams, but apparently I didn't last time. What I'm going to do instead is I'm going to actually also skip full, because full is not that useful of a practice problem, honestly. I'm going to do problem 5, And then since I skipped 3, I'll go and make it up with some other problem that I'll pull out of somewhere. We'll talk about that in a second. So this problem. This probably won't be on the final. I always do what's the final temperature of things being mixed, but it can be on the homework. So I want to go through one of these. And then I said I'll go back and do another heat problem after. It says, a family comes home from a long vacation with laundry to do and showers to take. The water heater has been turned off during the vacation. If the heater has a 50 gallons, okay, right there, we don't work in gallons. 50 gallons, well, I wrote that 1 gallon is 0.00379 meters cubed. So a 50-gallon hot water heater can hold 0.189 meters cubed. So we have a volume of 0.0189 meters cubed. And we heat this water with a 4,800 watt heating element. That means the power is 4,800 watts. These are all actual numbers. How much time is required to go from a temperature of 20 degrees Celsius to 60 degrees Celsius? Well, power. What I said about power is heat over time. Which rearranging, that means power times time is heat, or time is heat over power. If I want to find how long it's going to get, it's just how much heat it takes divided by the power. But I'm going to use the heat to change a temperature. And we know the heat of something changing temperature, that's mc delta T. So that means the time is going to be mc T final minus T initial over the power. Now, I don't know the mass. I know the volume. But we also know that density is mass over volume. And therefore mass is density times volume. And so if we have a volume of 0.189 meters cubed, and water has a density of 1,000 kilograms per meter cubed, that means we have a mass of 189 kilograms. And I'll say the time it takes is 189 kilograms times C, 4186 joules per kilogram degree Celsius. 60 minus 20 over 4800 watts. And the answer is 6,593 seconds. These are all real numbers for a real hot water heater. Just so you know, I did the conversion. That is 1 hour, 48 minutes, which is pretty reasonable. Usually they tell you to give it 2 hours. So, okay. So, here's my question for you guys. This is the end. I did skip this problem. I also skipped this one, but as I said, I'm not too worried about it. Because I skipped this problem, I'm willing to find another one to make up for it since it is the last class. But what I would do is what people want. So, would people rather I do another heat problem? If so, with ice or not ice? Or since it's the last class and you guys are here, I can solve some other type of problem too if you tell me what type of problem you want to see. What do you guys want me to do for my last problem of the semester? Anything? I'm going to take the silence to mean that you're happy and you don't need another problem. All right. That last one will be my last problem of the semester, and I'm not going to worry about it. You know what? Okay. If you're not going to pick one, I'll at least do this problem full. Because this might help on the homework. So let's do this to end. What it says is a steam pipe is covered with 1.5 centimeter thick insulating material. Okay, thickness. We actually use thickness as L in this chapter, which so it has a thickness of 0.015 meters. I know thickness is L just because I can jump ahead, but it's the whole T hot T cold thing. We use that's going to be the thickness. And what it says is it has a insulating material of thermal conductivity 0.2 calories per centimeters degrees Celsius second. Okay, that's kappa. That's really dumb units. 0.2 calories and centimeters? I gotta fix these units. I don't want to work in calories. I need to work in joules. Well, 1 calorie is 4186 joules. Cancel that out. And centimeters? I gotta cancel out my centimeters to get meters. Well, 1 centimeter is 100 meters. Oh, sorry, 100 centimeters is 1 meter. And so if kappa is 0.2 calorie per centimeter degree Celsius second, that's going to be 83720 joules per meter degrees Celsius seconds. So how much energy is lost every second when the steam is at 200 degrees Celsius and the surrounding air is 20 degrees Celsius? The pipe has a circumference of 800 centimeters, which I'm just going to C for now, of 8 meters, and a length of 50. Okay, I have two L's here, so let's just write thickness for now. Let's think about this. I'm talking about heat from two things touching. When we have heat of two things touching, that's the equation Q equals kappa A over L T hot minus T cold times time. In that equation, A is the area that is touching. Now, if I take a piece of pipe insulation that's going around a pipe, the area that's touching is going to be this square right here. The area that's touching is going to be the circumference, because that's what goes around it, times how long it is. Because this is a rectangle. When I flatten this out, I get a rectangle where this height is the circumference and this is the length. And so the area will just be circumference times length. My area will be circumference times length, circumference times length, or 8 meters times 50 meters, which is 400 meters squared. And therefore, the heat lost in 1 second will be kappa, 83720 joules per kilogram degrees Celsius second, times the area, 400 meters squared, over the thickness, 0.015 meters, times T hot minus T cold, times the time. And there you go. As I said, these won't show up on the exam, but they will show up on the homework. Make sure you do that last homework. Okay?
And that homework's due Sunday?
Sunday, yes.
Okay.
It's kind of a dick move on my part. I fully acknowledge it. It's not going to stop me from doing it, but I'll acknowledge it at least. That's why I get the big awards. Sorry. I just won the Chancellor's Award for Excellence in Teaching today, which was a weird thing to have happen. Okay, so that is the end of this semester. The only thing we got left is the final. If you need to ask me any questions, feel free to email me. I'm not going to do any office hours next week since I'm going to spend all day proctoring exams, and then we have the final. It seems kind of silly to have office hours, when the exam is Monday. But if you want to meet with me, let me know. But that is the end. Hopefully you enjoyed the class, at least somewhat. I apologize for being online. It's not as good as in person. Those of you who are taking it next semester, taking Physics 2 with me next semester, we will be in person. It will highly make the class better. I actually highly recommend people take Physics 2. It's a lot more interesting class, and honestly, it's actually a little easier. But that is where we are at. I hope you enjoyed. I hope you understand. I hope you got something out of this experience. And yeah, see you all around. Good luck on the final. Don't forget, it's Monday, May 10th at 3 o'clock. Bye.